We start today by a lecture about geomechanics, a very important topic relevant for underground hydrogen storage, but all other activities that we do in the subsurface. So I have the pleasure and honor to introduce Mark Zoback, who wouldn't need my introduction. Out of courtesy, I just read a few lines about him. Mark is professor of geophysics and the director of the Stanford Natural Gas Initiative at Stanford University. He has obtained his Bachelor of Science from University of Arizona and Master's and PhD from Stanford University, all in geophysics. He co-directs the Stanford Center for Induced and Triggered Seismicity and the Stanford Center for Carbon Storage. Dr. Zoback conducts research on in-situ stress, fault mechanics, and reservoir geomechanics. He has published 2 books, Reservoir Geomechanics. I'm sure many of you have it. I have plenty copies, Mark, to be honest. I distribute it to my students as well. Published by Cambridge University Press in 2007, which is now in the 15th printing. His online course, also entitled Reservoir Geomechanics, has been completed by about 12,000 students around the world. That was quite a big service to the community when you started and led this online education, Mark. We are all thankful for this. His new book, Unconventional Reservoir Geomechanics, was published again by Cambridge Press in April 2019. Dr. Zoback has received a number of awards and honors. He was elected to the US National Academy of Engineering, and in 2012 was elected to honorary membership of the Society of Exploration Geophysics. So Mark, we are all looking forward to hearing your lecture. Thanks very much for accepting our invitation.
Well, good morning, everyone. The title of this talk is a topic I've been talking about quite a bit for the last few years. At the Deep NL workshop you had, was that 2 years ago already? I gave a talk on this topic. And it's really because the expectations of those who are kind of taking an energy systems view of the transition from fossil fuels to decarbonized energy systems are counting on CO2 sequestration at a truly massive scale. It's not an exaggeration when you look at numbers like from the IEA, and they talk about a gigaton of CO2 storage by the end of this decade. You know, we're at 40 million tons a year right now, half of which is anthropogenic. So that's basically a 50-fold increase of anthropogenic storage expected in 8 years. They talk about 6 gigatons of CO2 by mid-century. 6 gigatons of supercritical CO2 is a volume that's 1.5 times the size of all the oil that is produced, distributed, and utilized around the world. So, when I talk to the public, I don't, I try not to use terms like gigatons and billions, and you can't get your head around some of these numbers. But when you say it's 1.5 times the size of the global oil system, that's impactful. They kind of understand how big these numbers are. And so it's a real huge geomechanical challenge. It's a challenge in many, many different ways. But that's not what we're here to discuss. So I've made a few small changes. No longer is it large scale, and we're not talking about CO2, we're talking about hydrogen. And my interpretation of this, and I've been kind of working on the talk as I've been listening to the presentations, and one of the real reasons to come is I've been working on a blue hydrogen project in the US, and I really wanted to learn more about hydrogen and what people were thinking about here in the Netherlands and the other countries you represent. I think Stefan made the point on Monday that maybe natural gas storage is a better analog for what we think about for a hydrogen economy than is CO2 sequestration. And I actually think that perspective is really quite helpful. And I've kind of used that, as you will see in my presentation. So that's how I've approached this from a geomechanical perspective. And I'm not talking about salt, because I know nothing about salt. And therefore, I have nothing to share of value. But we had several good presentations on salt, and it needs no, I don't have to embarrass myself by pretending I've worked on it. So there are 3 takeaway messages here. The first is if you're looking for places to put hydrogen, forget saline aquifers, okay? Just forget about it. And the reason for that are the geomechanical impacts of storing, anything that raises the pressure in these saline aquifers, even a small amount. And that's where the earthquake story comes in, and there was some references to earthquakes on Monday during the discussion session, and I didn't say anything because I knew I'd be talking about it today. And so I do think there's a responsibility to kind of close the loop on that. Not everybody has heard this story, but we've been studying these issues very intensively for a decade or more in the U.S. and Canada. It's a big deal in Argentina right now, China, for example. And so I do want to talk about why, as you think about sites to store CO2, forget about saline aquifers. Quite different than what you heard from Sarah on Monday afternoon, but I'll make the case. Lesson number 2, as the depleted gas reservoirs can potentially work, and there's certainly a lot of issues, and some have been raised. And I'll talk about that from a geomechanical perspective. In other words, what happens when you actually deplete one of these reservoirs? Okay, we have a reservoir, you explore for it, you characterize it, you drill a few holes, you appraise and eventually develop these gas resources. And you have a lot of depleted gas reservoirs in the Netherlands, and so it's, along with salt caverns, it's an attractive possibility, and I want to talk about why. And then I think Tony brought up yesterday the fact that when you're using a depleted reservoir, it's not the same reservoir that you initially were producing from. And I'll talk a little bit about some of the characterization issues from a geomechanical point of view that have to be considered. And finally, I want to say a few words about production-induced seismicity in Groningen, because you do have a big depleted gas reservoir. But it's a very unusual one because of the depleted earthquakes that have occurred. And I was here in the Netherlands 3 weeks ago at a conference on MMAX, how big might the biggest earthquake to occur in Groningen be. And as all of you know, the reservoir is slated to be shut down next year, I believe, and then production is way down already. It's a complicated issue, especially with the war in Ukraine and European gas supplies. I'm not going to get into the politics of it. I'm going to talk about what's happening in Groningen and why from a geomechanical perspective, because it is I'm going to make the case that depleted gas reservoirs should be taken very seriously as an opportunity for hydrogen storage, but the most well-known and largest depleted gas field in Europe is a place which is so seismically active that production is slated to be shut in, even though there are 700 billion cubic meters of gas that are available, to get you through the next winter. A point I'm sure you're aware about. But when you think about depleted gas reservoirs and their potential for hydrogen, my story is very simple. Don't worry. Be happy, okay? You have opportunities, and it doesn't mean there's not hard work to do, but you have options and you have a path that could provide opportunities for gas storage, hydrogen storage, that could be very attractive. So let me talk a little bit about CO2 to kind of get us into this topic, and then go from there. So in Sarah's presentation, following Sam's presentation, she talked about these regional assessments of CO2 storage capacity, and this is one done by the United States DOE of North American capacity. And the numbers are mind-boggling. I mean, there's so much volume in these saline aquifers. The table there, which you probably can't read, and even I can't read right now, The mid-range estimate is 8,000, gigatons of capacity. And the thing I disagree about with Sarah's presentation, she said, well, look at this tremendous capacity, and there are these, projects going on around the world. It's smooth sailing from here. I'm very concerned because I think this is extremely misleading. These assessments are helpful. It's a starting point, right? This is where the saline aquifers are that we need to look at. But just to give you an idea of where we are, as a as a society who wants to increase CO2 storage to help decarbonize. And by the way, there's nothing new about CO2 storage. I mean, I think it was highlighted in the 2005 IPCC assessment. But the reason it's taken prominence and more emphasis on CCS as time has gone on is because it's a truly negative carbon technology. I mean, you're not just lowering the rate at which you're generating carbon by switching to more efficient systems and everything else, but even there's a carbon signature with everything we do. It's actually negative. I mean, it makes carbon go down. And therefore, when you're doing this juggling act of all the different things we have to do to decarbonize the energy system, CCS is becoming more and more important because it's truly negative. And so that's understandable. But we have to, characterize the capacity of the subsurface. And simply equating pore volume with capacity is not correct because there's something in those pores. They are saline aquifers. They're saturated with saline fluid, okay? Now, in the petroleum industry, there has been something called PRMS, Petroleum Resource Management System, I think. And the way to think about it, it's a formalism so that every time an oil field is bought or sold, or an operator is borrowing money, or all the financial transactions have to be done on the basis of how much oil is in place, how much can be recovered, and therefore what is the value of the asset that is being discussed. And so there's this PRMS, Petroleum Resource Management System, that's widely adopted, used around the world. There are large consulting companies that you hire and you say, okay, I want to sell this field, I want to buy that one. And they are like independent, certified companies who are well respected and they have no financial, role in this except to do the assessment. And they provide that information to the people involved. So the Society of Petroleum Engineers undertook the exact same effort for carbon storage. And the idea is if you are a company and you are going to store carbon in the subsurface and you're going to borrow money or you're going to go into some sort of financial partnership, you needed the same kind of assessment. You needed an independent way of assessing what the storage capacity actually was. And so this SRMS system has been developed and, through a very complicated committee structure and gone through review and public comment and all the rest. So it's there and it's available, but it's really not been used, and of that enormous resource you saw in North America or this, the similar atlases around, this very, very small percentage of these potential saline aquifers have actually been characterized in any way whatsoever. And there's never been an economic incentive to do it. Nobody was collecting seismic data, nobody was drilling wells, nobody was doing well testing, all the things you would have to do to kind of understand how much CO2 might be injected at a given place. So there's a huge characterization effort. But there's another that needs to be carried out. But there's another issue, and that's the seismicity issue that has really plagued this. And I think I want to talk about this just to frame the issue based on what is, a tremendous amount of experience that has been obtained mostly in the U.S. over the past decade. And I want to start by talking about basal aquifers. A basal aquifer is nothing but a sedimentary formation. Think of it as a porous sandstone that occurs at the base of the sedimentary section and sits pretty much directly on crystalline basement. Okay, not too complicated. And we've gotten very involved in studying earthquakes in Oklahoma, which and the Fort Worth Basin, the area around the Dallas-Fort Worth area. 7 million people live in the Dallas-Fort Worth metropolitan area, related to unconventional oil and gas development. But the same principle is applicable in the CO2 storage projects in Decatur, Illinois, and the Quest project, which they're on the list of successful projects. Well, they're successful, they're happening, but there are issues, and I want to tell you about that. So the story in the U.S. is really pretty easy to understand. You're probably familiar with a lot of it. This shows a plot made by my colleague Bill Ellsworth since 1970 of the cumulative number of earthquakes of magnitude 3 or larger in the lower 48 states. And magnitude 3 is used as a threshold because the seismic network that's been operating since, 50 years now, since 1970, has been able to detect a magnitude 3 earthquake anywhere one would occur. So we haven't missed any earthquakes. If you go to, if you started to count the magnitude 2 earthquakes, you'd miss earthquakes in some parts of the country just because there's no network there. And what you can see is that it's a relatively steady rate in the mid-continent of the U.S., and that's because earthquakes occur everywhere from time to time. But in the early 2000s, we began to deviate from that long-term trend. The number of earthquakes were increasing. This is the same time that we started horizontal drilling and multi-stage hydraulic fracturing, and the immediate response of the press and the public is that fracking is causing all of these earthquakes. Okay, that turns out to be fracking is only a very small part of the story. But around 2013, 2012, 2013, you can see the number of earthquakes just dramatically accelerated. Something is going on. Now, if you look at the last 25 years and kind of blow up, you can see that recent exponential rise much more clearly. But the great majority of that seismicity was occurring in Oklahoma. And so 10 years ago, I was briefing the governor of Oklahoma, and about what on earth is going on in Oklahoma. And the title of my presentation, I prepared a PowerPoint and I prepared handouts. Don't meet with governors every day, and it was really wonderful. We went into a conference room, we sat next to each other, and then I just could page through the PowerPoints, and she paid close attention. She asked very good questions. But the title of my presentation was The Curious Case of Oklahoma Seismicity, because of the movie that was out about the curious case of, referring to Brad Pitt's usually a good move. Anyway, and the reason Oklahoma was so unusual, and when I was in graduate school, the induced seismicity experiments in Rangeley, Colorado, and the Denver Arsenal, which some of you may have heard about, which was really the beginning of the modern era of studying induced seismicity scientifically. I was a graduate student, and it was a really exciting time. The idea of taking principles from the laboratory and then applying them to the earth. It affected me so much. That's basically been the common theme of everything I've done during my career. But Oklahoma was different. And the reason Oklahoma was different is because the whole state lit up. Now, this is from the first paper we wrote in 2015. The red dots are the earthquakes. So, and there's a scale there, a 100-kilometer scale. So Oklahoma's a fairly big state. It's probably about the size of the Netherlands, I guess. And the whole north-central part of the state was lighting up, all those red earthquakes. And there were various things going on at the time. The blue X's represent water injection wells, and I'll show you a geologic diagram in a few minutes to explain a little bit more detail. but that is where salt water is being injected into the subsurface. And so instead of there being sort of an earthquake in a place that was unexpected and some anthropogenic activity nearby, and then the question is, well, is there a relationship or is it a coincidence? You see the whole state lighting up at once. And that was really quite remarkable. There'd never been anything like this, that had ever occurred that we knew about. At the same time, oil and gas activities, which are the little the black tick marks, those are enhanced oil recovery operations where water that is produced with oil is just recirculated back into the same producing formation. Okay, so it's just, you produce oil and water, you separate them, you put the water just back into the same formation. And so what was the physical and spatial relationship between these processes? Now, Oklahoma has a long history of being an oil-producing state. It's an important part of their history, their culture, their economy. But, what was happening was a great concern. So this shows the cumulative number of earthquakes as a function of time. I think we used magnitude 2.5 for this plot. Prior to 2009, there was one magnitude 4 earthquake every decade. Now, a magnitude 4 earthquake is going to be widely felt, but is really almost impossible to cause any kind of significant damage. Okay, a little bit of shaking, something might happen, but you're certainly aware that the earthquake's occurring. And but when it happens once a decade, you just get on with life. You don't give it much thought. When it's happening every few days, it's something else again. And so these earthquakes in the north central part of the state, this is where most of the people live in Oklahoma, and these earthquakes were being felt by 1 million people or so every few days. And so, what on earth is going on? And you can imagine then the debate between the producers. Who? Us? We've got nothing to do with this. Of course, it wasn't the oil and gas industry. And then more, people taking dramatically the other side. Well, after correcting 2,000 errors in the state database that is related to water injection and in these different wells and all the rest, we sort of got to the bottom of it. And what it turns out is oil prices were very high at the time, and there were a couple formations. These two black layers schematically represent this Mississippi lime. It was a carbonate that was traditionally known as an oil-bearing carbonate, but produced so much water it was never economic. But a couple of enterprising small companies had this idea. They said, well, if water is the problem, let's solve the water problem before we start producing oil. And so what they did is that they identified this Arbuckle Formation. So the Arbuckle Formation is a thick karstic carbonate that sits right on top of crystalline basement. It's even underpressured. And it was used for disposal for many decades. Various types of small-scale disposal had gone on. And the Arbuckle outcrops at an elevation about 200 meters lower than the elevation of north central Oklahoma, so it's underpressured. You could put water in it, it just falls in under its own weight. And so they drilled large diameter water disposal wells down into the Arbuckle before they drilled their production wells into this Mississippi lime and the comparable formations. And so as soon as they started producing all these vast quantities of water, they'd already solved the problem. They separate the oil and water, send the water to these Arbuckle wells, and all those blue dots, all those blue crosses you saw in the previous slide were something like 600 injection wells. The largest, some of them were injecting, 80,000 barrels a day. If you remember the undersea photographs of the Macondo well blowout, the gushing oil out of the seabed, that was about 60,000 barrels a day. And so, that was happening in reverse, and that's how big these water disposal wells were. And they injected a few billion barrels. A barrel is 6 barrels per cubic meter, so this is 500,000 cubic meters of water were injected in just a short period of time. And what that did is it raised the pressure in the Arbuckle. Not very much. It's thick, it's porous, it's permeable, it's regional in extent, but it raised it, and I'll show you the result of hydrologic modeling in a second. And that increase in pore pressure was transmitted to faults down in the basement rock. Now, the basement is 1.2 billion years old in this area, and so there's lots of fractures and faults inherited over, geologic eons. But some of those fractures and faults are active today. Most are not. Most are sealed up. But some are active, and those turn out to be permeable. And so that pressure was transmitted to these faults, and all the earthquakes were then occurring down at depth. And it turns out, this is some research we had done in a much different context, but was useful, is that when you look at crystalline basement like this and you see all of these faults, it turns out that it's really easy to figure out which ones are permeable today and which ones have been sealed up over geologic time, and it's whether or not they're active in a geologic sense. So those that are just at the right orientation to the current stresses and might move every 10,000 years, every 100,000 years, there's a mechanical process that maintains the permeability of the fault, whereas if they're just sort of sitting there for hundreds of millions of years, they just seal up due to water-rock interaction and precipitation and various kinds of processes like that. So the earthquakes are down here, the injection is up there, and the oil production is up there. Now, this is a hydrologic model that we developed in trying to understand what was going on. And so, it was a fairly straightforward process of developing this model. It was a layered model. The only heterogeneity in the model is this big, huge north-south trending fault, the Nemaha Fault, which goes hundreds of kilometers to the north, and it's just a very old geologic regional structure, was considered a flow boundary, so that's a sealing fault. And so this depression, this increase in pressure that you see on the right side is due to injection on the east side of the fault, and the increase in pressure you see on the left side is due to injection on the left side of the fault. And the dots are the earthquakes, the yellow are the largest earthquakes, but it's the scale that's important. These are megapascals, so the biggest pore pressure increase was about 2 bars, estimated at depth. A very small pressure change is all that it took to trigger these earthquakes. Okay, so yes, the pressure went up in the Arbuckle, massive amounts of water were put into it, but it was such a large aquifer that the pressure change was extremely small, but still big enough to result in all of these earthquakes. The largest earthquake was a 5.8, a rather sizable earthquake. Could have caused significant damage, but it occurred in a relatively remote area. Now, this isn't exactly a surprise, because we've known that intraplate earthquakes occur, almost everywhere. And these are a couple maps that are a little dated now, originally made for a paper I published about 2011 when all of this was, becoming widely known. And, you see here in the United States, earthquakes distributed almost everywhere. Here in South Asia and China, you see earthquakes occurring almost everywhere. Some areas are really active and some areas are much less active. But even in relatively inactive places, you get very serious earthquakes. And of course, there's a very long history of earthquakes in China, for example, and some of the biggest and most devastating earthquakes in human history occurred in East China, where relatively few earthquakes occur. And the way to think about these kinds of maps is the earthquakes are telling you how fast the crust is deforming, right? An earthquake is a release of strain energy, right? And at greater depth, where the rocks are hot in the lower crust and upper mantle, the Earth, there's deforming ductily. But in the brittle crust, the only way the Earth can deform is through a brittle process. So the earthquake rate is telling you the strain rate. It's not telling you the stress level. And the way we know that is, well, we've measured it in places, but these red dots represent earthquakes. So here in the Indian Shield, there are a couple of red dots up in the Canadian Shield. These are really, the most stable parts of continental interiors. These are places where the building of a dam, the impoundment of a reservoir, has resulted in earthquakes at depth. And, most dams are not very high. The pore pressure change, as transmitted down into the basement is extremely small. So reservoir-induced seismicity was a clue all along that the Earth's crust is critically stressed. There are some faults just ready to slip. Most are not. Most of the faults in the crystalline basement are dead, inactive, unimportant, but some are going to produce earthquakes, again, every few thousand years, tens of thousands of years, hundreds of thousands of years, whatever. In a geologic sense, they're still active, and if you change the pore pressure, you take one of these faults that's going to slip sometime in the future, and by raising the pore pressure, you reduce the effect of normal stress, and you allow that fault to slip today. So you're accelerating the release of strain energy. The pressure is not causing the earthquake. The pressure is allowing energy to be released that would be someday released as a natural geologic process. You're just moving it forward in time. And this is something I was, of course, working on as an earthquake scientist for many years. And then as I got interested in CO2 sequestration, I began to kind of worry about this. And my colleague Steve Gorelick and I wrote this paper published in 2013 that was quite controversial because we pointed out that this is something that could affect CO2 sequestration. And boy, we took a lot of grief about this. People say, well, come on, it's important. We got to get to work on this, and we don't want to worry about earthquakes. We don't think they're going to be that important. And so we wrote this paper, and like I said, got a lot of pushback. But I would say in the 10 years since we published this paper, all of the earthquakes associated with water injection have actually proved our point. Now, the one thing about this paper, and it's interesting, some of you are too young, but others not, to look at things you'd written maybe 10 years earlier or longer, and what would you write the same paper today? And I think we'd write the same paper today. But the thing I would change about this paper is we pointed to these earthquakes as a potential threat to the seal of the CO2 reservoir, okay? And I think that's still an issue, but public perception, I think, is a much larger issue. If the public associates CO2 injection with earthquakes, they're going to associate it with a hazardous activity, and they're going to oppose it. And we don't do anything without public consent or anything at scale, or you don't do it for long. So if you lose the trust of the public, the show is over. And so now I think we put a much larger emphasis on that. And the big problem with respect to earthquake size is when the earthquakes occur down in the crystalline basement. So the top two diagrams, the paper on the left is the first paper written about any of the triggered earthquakes in Oklahoma. The network wasn't very good. The injection, the yellow, it represents the Arbuckle there. But the earthquakes are down in the basement and in the Arbuckle. But the diagram on the right represents a decade of improved seismic coverage, improved velocity models, improved refinement of knowledge of where the earthquakes are. And what you can see is while the injection is in the Arbuckle, the earthquakes are concentrated 4 or 5 kilometers down into the basement. On the left is a Canadian example. On the right is Arkansas. Dallas-Fort Worth area is exactly the same. The water is injected into a basal sedimentary unit. The fluid pressure penetrates into the basement, triggering the release of energy that's already in the earth and that would someday produce an earthquake. So this is what we mean when we say triggered seismicity. Okay? We talk about induced seismicity, triggered seismicity. There's a real difference, and the difference is if you're inducing earthquakes, say because you've built a mine, the mine excavation concentrates stress around the opening, and that maybe produces an earthquake. You're inducing it. You're putting the strain energy in. But when you're triggering the release of strain energy, you're actually, triggering the release of energy that's been accumulating for very long periods of geologic time. And the reason this is so critical is this diagram, and it's a little bit complicated, so let me walk you through it slowly. Over the years, seismologists in studying earthquakes have develop scaling relationships. So this is kind of like the most zero-order scaling relationship. The bigger the earthquake, the larger the size of the fault that slips. Okay? Now, you know, Tony and I live practically on top of the San Andreas Fault. It extends from, Mexico all the way up to Northern California. It's 700 kilometers long. Every few hundred years, there's a magnitude 8 earthquake, but there's 1 million magnitude 2 earthquakes for every magnitude 8 earthquake, okay? And a magnitude 2 earthquake means it's just a small patch of the fault that slips. So the x-axis here is how big is that patch that slips. The y-axis is how big is the earthquake. And this, and you're kind of, you kind of know the numbers. You start feeling earthquakes at 2 and 3 and 4. As I said, it's widely felt, but no damage. And, you start to get damage around magnitudes 5 and 6s, and anything, magnitude 6 and larger is, a potentially severely damaging earthquake. Scientists tend to actually not use magnitude. We convert to magnitude to talk to the public, but we talk about the moment of an earthquake. The moment is basically the area times the slip times the shear modulus. Okay, it's the literal amount of energy that's being released, and so they're equivalent. The diagonal line represents the seismologically determined scaling between size and the slip patch. So if you actually, experience, say, let's just say a magnitude 5 earthquake, and you go over here and the red area, that it depends on what the stress drop is in the earthquake, but so the width of that diagonal bar represents variations of different kinds of earthquakes with different stress drops, but the message is the same. If you've got a magnitude 5 earthquake, a fault that is slipping over 2 kilometers or more is required, right? And you need a fairly large fault. So the earthquakes you're worried about require fault slip over patches that are kilometers in size. So you don't get that in a sedimentary layer. You only get that, and usually the sedimentary cover is 1 kilometer or 2. You get that in the basement where these faults, go quite, potentially quite deep and are sort of natural faults that are going to be activated. So basically, the way to think about it is if you trigger earthquakes on a small fault, you get a small earthquake, and if you trigger earthquakes on a big fault, you get a big earthquake. If it's the big ones we're worried about, we're really worried only about the earthquakes that are occurring down in the basement. If the faults are limited to the sedimentary section, they may be detectable, they may be 3, magnitude 4, but they're not likely to be large damaging earthquakes. And so these relationships have been very well established in numerous studies, and our contribution was simply to generalize it. By the way, you probably are aware of the fact that horizontal drilling and multi-stage hydraulic fracturing triggers lots of little micro earthquakes. Those tend to be magnitude -2, and they correspond to slip on patches of faults that are about 1 meter in size. So these micro earthquakes that occur during hydraulic fracturing are tiny little things which release the same amount of energy as a gallon of milk falling off the counter and hitting the kitchen floor. They're really pretty inconsequential. But it's the basement earthquakes that are problematic. So let's look at these quote-unquote successful carbon storage projects. This is Decatur, Illinois. There's a corn ethanol plant, I believe, that generates CO2 right in the town of Decatur. A few tens of thousands of people in the Illinois basin. And when they started the injection, what you can see is a map of the earthquakes, but there's a schematic diagram, and what you can see is the injection was right into the basal part of this Mount Simon sandstone, and the earthquakes are occurring in defining faults that are just going down into the basement. Now, this project is still going on. They're injecting a few 100,000 kilograms of CO2 a year. It's not a very big project, but it's ongoing. And the earthquakes are very small. The biggest earthquakes have been a little bit larger than magnitude 1. But the operator of the corn ethanol plant has argued that as soon as an earthquake that's felt by the people of Decatur occurs, which probably magnitude 2 earthquake or something like that, it's not going to be a significant earthquake, that they're gonna probably stop the CO2 injection because of public concern. So they've moved the injection zone up to a higher level to try to prevent the pressure change associated with the injection from getting transmitted down into the basement. And the earthquakes have, there are fewer earthquakes, but they're persisting, and the pattern of earthquakes hasn't changed very much. And I have a long-standing bet with someone in the CCS business that sooner or later this project's going to get shut down. It's not going to get shut down because of an earthquake that's going to hurt anybody, but the earthquakes will start being big enough to be felt, and that'll be the end of it. The Quest project, a shell project in Canada, they're injecting, I think, a little bit less than 1 million tons a year, which is kind of a characteristic size for a lot of these projects. They're injecting into a basal Cambrian sandstone, which I'll show you a map of here shortly. And it's not very widely known, but it is in the public domain that earthquakes are occurring, and it's exactly analogous to Decatur. It's 2,000 kilometers away, or at least 1,000 kilometers away. And we're seeing faults down in the basement being lit up by this injection into the sedimentary section. And you go back to this atlas and you say, well, what are these big sedimentary saline formations that are identified that contribute so much to this presumably large capacity? And this mid-continent, you can see the border between the U.S. and Canada going right through there. So this is an enormous structure. This is Quest. This is Aquastor, another project that's going into this formation. And I would argue that it's one thing for these little projects to be going on, but the possibility of storing thousands of gigatons in these basal formations has to be reconsidered. And I would argue that no CO2 should be put into a basal sedimentary unit unless there's a bottom seal. We always talk about the top seal, right? You don't want the CO2 migrating vertically, but you don't want the pressure propagating downward. So I think the first thing I would do with these atlases is throw away these basal sedimentary units. Now, that's not the only issues of concern. So let's talk about the Permian Basin of Texas. And we'll start in the Delaware Basin. So this is West Texas. You can see the corner of New Mexico here. The border with Mexico is sort of down here. And this is an area where I don't know the exact number. It's over 10,000 wells have been drilled, horizontal wells, multi-stage hydraulic fracturing. They produce a lot of water. That water is being injected and producing earthquakes. So we're going to start by talking about the Delaware Basin. So the Permian Basin is broken up into 3 main units. The Delaware Basin is to the west. Then there's something called the Central Basin Platform. And then the Midland Basin is to the east. So we're going to first talk about the Delaware, and then we're going to talk about the Midland Basin. Now, the area involved here is enormous. I saw the outline of Texas superimposed on the outline of Western Europe, and this is sort of Netherlands, Belgium, a bit of France, and a bit of Germany combined. So it's a big area. Okay, in the Delaware Basin here on the west side, this is the Delaware Basin, and there is unconventional development everywhere. There is water injection everywhere, but there are only earthquakes in the area where there has not been previous production from the injection zone. So let me say that a different way. So the injection is into a formation called the Delaware Mountain Group, okay, a group of sedimentary formations. It's being used everywhere in the basin for water injection right now. In the past, the Delaware Mountain Group was an oil-producing region in much of the Delaware Basin. And the purple dots are showing you where oil or gas has been produced from the Delaware Mountain Group. Today, we're not producing oil anymore, we're just injecting water into it. The place where the earthquakes are occurring, which is in red, is the place where the Delaware Mountain Group is a saline aquifer. The reason no oil and gas were produced there is because, the oil migration, is all sort of up dip, and this is where it's just a saline aquifer. So the way to think about this is these red earthquakes are caused by water injection into a saline aquifer. Water injection into a depleted formation is not producing earthquakes. Okay? So the earthquakes are only where there's been no previous production. When we look at those earthquakes, they're all extremely shallow. Okay? They're right in this Delaware Mountain Group, which is exactly where the injection is. Okay? At depths of only 1 to 2 kilometers. One thing I didn't mention is the ground is deforming. The ground deformation is studied with INSAR. The INSAR signal has been inverted, and the interpretation of the INSAR data requires slip-on faults, which happens to be just at the exact same depth of the earthquake. So it's a very nice story. The papers have just come out. This paper is one of my papers in 2021. The data comparing the earthquake depths and the depths of slip inferred from the INSAR is just out this year. So a very simple story. It's very well constrained to shallow depth and the depth at which the injection is occurring. And our colleagues at the University of Texas have gotten a lot of 3D seismic data, and they've met. So this fault up here shows the earthquakes, some of the INSAR deformation, and the faults that have been inferred, along with some of the stress data that we've pulled together. But the important thing is that these earthquakes in the Delaware Mountain Group are occurring on faults that are restricted to the Delaware Mountain Group. In other words, above the Delaware Mountain Group, there's salt, and so the faults are not propagating upward. And below the Delaware Mountain Group, there's a lot of shale, and that creates kind of a different stress state, and that's kind of a fault barrier. It's a story I don't want to get into in any detail here. But the point is, there's shallow earthquakes on faults that are geometrically limited in size, and therefore the earthquakes are limited in magnitude. The biggest earthquake that's occurred is about magnitude 3.5. Right? Because, of the, few hundred meter thickness of this, and the earthquakes don't occur any shallower and they don't occur any deeper. The other interesting thing about this is also work from the University of Texas that's been just released. The pressure change that has triggered these earthquakes is extremely small. In fact, blue is close to zero, okay? So it could be just a few bars. Okay, but it's close to zero. So some of these earthquakes are occurring where there might be 10 or as large as 20 bars in the most intense region. But in most of the area where the earthquakes are occurring, the pressure change again is really small in this Delaware Mountain Group. Why? Because the Delaware Mountain Group is a brittle sedimentary rock which is behaving just like the brittle rocks in the basement, but the difference is it's geometrically limited by the geology, right? There's salt above it, soft rocks below it. The earthquakes occur, but they can't propagate. They can't be big earthquakes because the slip is confined. Now, that's not the only thing that's happening, and I keep getting told, the oil and gas companies, they're on top of all these earthquakes. They know what they're doing. And no, they don't. Trust me. Because right now they're repeating Oklahoma. And they're repeating it in the Midland Basin. That's now the eastern part of the Delaware. So I was talking about this before, okay? And this is near the towns of Midland and Odessa. And what's happening here is the earthquakes have, gotten very more frequent. They've been injecting at shallow depth for a long time. That's the yellow line. But what they started to do is they started to have too much pressure in some of these shallow formations, and they started injecting deeper into a formation just above the crystalline basement. And as soon as they did that, that's the blue line, the earthquakes have started. The earthquakes are defining regional scale faults that are just at the critical angle to the regional stress field, and so they're now inducing larger earthquakes on regional scale faults by deep injection. So now, instead of the disposal zone being way up here, the disposal zone is just above the basement, and if you get two seismologists together, they'll never agree about where the earthquakes are. But this is the Texas version of where the earthquakes are. This is the Stanford version of where the earthquakes are. They're more consistent than normal, but they're really quite shallow. So it's just like Oklahoma. The injection is just above the basement. The earthquakes are a few kilometers down in the basement, and the earthquakes are bigger. They're getting 4.5 magnitude 5 earthquakes with frequency, and they haven't stopped yet, but the regulators are really very concerned, and they're, as we speak, there have been regulations, and there'll probably be more, which is strongly encouraging the operators to stop doing this. And yes, it's harder to find places at shallow depth to do the injection, but you really need to do it, or the earthquake situation is just going to get worse. So while things haven't changed, they are changing, and I think changing in the right direction. There's a general understanding that what has been occurring should not continue. Okay, so that's what happens when you inject into a saline aquifer. Okay, if they're brittle and you change the pressure a little bit, you can get earthquakes. And so, lesson number 1 was forget saline aquifers, and I strongly recommend that. It doesn't mean that all saline aquifers are bad. A lot of saline aquifers could be good if they're not very brittle, and if you do an adequate characterization, before you do the injection, they may turn out to be fine. But it's going to take you some time, and it's going to take you some money to actually do the work that you need to do to characterize them, and fully, both geologically and geomechanically. So why am I so enthusiastic about depleted oil and gas reservoirs, both for CO2 sequestration and for the potential of carbon storage? It's because of poroelasticity and what happens when you deplete a reservoir. So this figure is from my first book, and it's about as far as I've gotten in my understanding of poroelasticity. It's a very highly evolved theoretical framework, and it's just beautiful. It's very hard to implement is the problem. So to think about it simply, think about a laterally extensive reservoir. All that means is the horizontal extent is 5 to 10 times its thickness. And so that's almost always the case. Otherwise, it wouldn't be economic. The overburden is going to press down on this, so we're just going to assume it's horizontal, infinite in extent, but just large. And you're going to change the pore pressure by producing hydrocarbons. And that means that the stress in all directions is going to go down equally. It is just assuming everything's isotropic and elastic. You solve this problem elastically, and the change in the horizontal stress is related to the change in the pore pressure using two material properties. One is Poisson's ratio, and the other is called the Biot coefficient, alpha. The Biot coefficient is telling you, this alpha is telling you how compliant the rock is. Alpha for soils is 1. And the reason is, in the soil, the grains of the soil are very stiff, but the soil aggregate is very compliant, right? Because the grains move with respect to each other. So the bulk modulus of the bulk is very small. The grains are very stiff, so alpha is 1. And so in poroelasticity, effective stress means you take the stress and you just subtract the pore pressure, and that's the effective stress. And that's what was worked out in the 1930s by Terzaghi, who was a soil mechanics guy. It turns out if the rock is stiffer, right, the grains are cemented, alpha is going to be less than 1. Okay, so alpha is a material property you need to know. And for a soft soil, assuming it's close to 1, a soft rock, very porous, compliant, you can assume it's very high. Poisson's ratio, something like 0.25 is quite reasonable. It could be 0.2, it could be 0.3, okay? When you plug this in to this formula, you determine the change in stress with respect to the change in pore pressure. And that's sometimes called A, or it's the stress path. So in other words, as the A times delta P is telling you how much the stress is going down, the horizontal stress, the vertical stress is not changing as the pore pressure changes. So if you plug in 0.25 and 1, the stress path is about 2/3. So if your pore pressure goes down 5,000, let's say 6,000 psi, the stress goes down 4,000 psi. Pretty simple. So about 20 years ago, Alvin Chan, a former graduate student, and I were looking at this. And so we decided that we had to represent laboratory data a different way because, laboratory people do experiments. They have all sorts of graphical illustrations of how rocks deform and under changing stresses. But we had to translate it to ways in which, say, reservoir engineers or anybody else who's interested what's happening in situ could understand it. So we developed something which we'll call DARS. I'll get into that in a little bit more detail to understand how pore pressure and stress evolved and what it meant in terms of the change in reservoir properties in two ways. How is the reservoir going to compact? How's the porosity going to change? Okay. And does the change in stress with pore pressure encourage or discourage faulting? Okay? And we're going to talk about normal faulting. Normal faulting was the case we were worrying about. Normal faulting is what you care about here in the Netherlands, so normal faulting is good. So the way to think about this diagram is here's pore pressure, right? So pore pressure is going to start high and it's going to go low. Here's stress. The vertical stress that's just the overburden, right? 23 megapascals per kilometer or whatever, okay? And this diagonal line represents normal faulting. So for those of you who understand Moore diagrams, it's basically telling you that the Moore circle is touching the frictional failure line, okay? In other words, it's saying when you're at any pore pressure, if this is the vertical stress, this line represents the smallest value of the minimum horizontal stress. If it gets it can't be below that because normal faults will start to slip, okay? So that's the limiting value. So you always have to be operating somewhere in this gray zone, okay? So that's the whole point. And you're going to start somewhere, and then as you take pore pressure out, as you move to the left, the slope of that line is the stress path, okay, according to this equation. And so what is the slope of that line? Well, the slope of that line is shown here. Here's the stress path. The vertical axis is the stress path. The horizontal axis is the Biot coefficient. The diagonal lines is Poisson's ratio. And over here on the right, we show some reported stress paths from the literature. And we use a normal font when we agreed with the authors. We used an italic font where we're not quite sure that they were talking about the change of stress and pore pressure at one place, or they were looking at pore pressure changes maybe in one part of the reservoir and stress changes in another. They report it as a stress path, so we report it as a stress path. Okay? So this is where you are. If you know what the Poisson's ratio are, what the Poisson's ratio is, and you know the Biot coefficient, you can say, well, my stress path is going to be 0.5 or 0.6 or 0.7. But the interesting thing is the slope of this line is 0.67. It's just the way the math works out. Okay, and that's why we have this dashed line here at 0.67. Why do we do that? It says if you start here, okay, so here you are at a given pore pressure, a given stress, you're not in a failure condition, okay? If your stress path is, say, 0.5, then you're on something like this green path, and as you deplete, you get further and further away from normal faulting. In other words, your depletion is stabilizing the faults, which is almost always the case, right? We don't often see earthquakes associated with depleting reservoirs. However, if the stress path is steep enough, what you have is it's stable, 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 and then after a certain amount of depletion, you hit the frictional failure line. And with a steep stress path, you can actually have depletion-induced faulting. And then, of course, you can't cross that line because the faults keep moving and moving. You just slide down along it. So any stress path above 0.67 is potentially destabilizing faults if you deplete enough. If you only depleted a little bit, nothing would happen. But if you depleted enough, you'd eventually could trigger earthquakes, and then that could keep going, okay? Now, the reason we worked on and then the porosity part of it. Okay, so what do these contours represent? The contours represent irreversible porosity loss, right? You raise the effective stress, and the rock's going to want to compact. And so there's a theory it started with soil mechanics at Cambridge, and it's called the Camp-Clay model. And this is it's like a Moore diagram. This is the invariant of the compressive stress. This is the invariant of the shear stress. And these ellipses represent the loss of porosity. So the way to think about this in a lab sense is suppose you took a cylindrical sample and you just subjected it to confining pressure, no shear stress. Just confining pressure. Well, you give it a little confining pressure, you move out along this axis, nothing happens. You lower it, raise it, lower it. The rock is just elastic. You lose a little porosity, comes right back, it's elastic. But if you compress it too much, you begin to damage the framework of the rock, right? And it begins to compress permanently, and you don't get the porosity back. And that's what this end cap represents. So this rock had about a 40% porosity. This is a chalk. And when you get to, 22, 23 megapascals, 220 bars, you would hit this end cap, meaning that you're reducing that 40% porosity rock to 39%. And if you reduce it, that porosity doesn't come back. You go back up there, nothing happens. But if you go to a higher stress, the porosity gets reduced to 37%, 34%, and so on. So it's just describing compaction. The reason these things are elliptical and kind of have this backward curve is the fact that this compaction, if you had a little shear stress at the same time, occurs at a lower confining pressure. So you get the same compaction at a lower confining pressure if you have some shear stress. And then this could be represented very nicely with these mathematical ellipses that were worked out in this Camp-Clay soil mechanics model. So we like that model a lot because we're interested in compaction, not only faulting. And so, but it's hard, it's hard to do experiments in this space and then just mentally say, well, what it means about the reservoir. So what Alvin and I did, which means I had the idea and he actually did it, is mathematically transform these end caps into this reservoir space. So this is exactly the same kind of representation, but now we can talk to the reservoir engineers about what's happening to the pore pressure and what's happening to the stress and how the reservoir conditions are likely to change as the reservoir depletes. And as I illustrated in this figure, that's what this represents then. You start somewhere, and then you deplete somewhere, and here, if you had a stress path of 0.5 or something like that, you say, well, we're not going to get earthquakes, it's more stable, but we're going to go from about 40% porosity to about 34% porosity, okay? And that's, reservoirs compact, and that's what's expected, okay? So it was this transformation we found quite useful, and we've actually seen it used by a couple of others in the 20 years that it's been out there. And in my textbook, I illustrated it. This is a field in the Gulf of Mexico. The reservoir is active normal faulting in the Gulf of Mexico. The reservoir is very interconnected, so all these different wells drilled from different platforms are showing sort of uniform depletion as a function of time. The least horizontal stress is, very easy to determine. You just do it with hydraulic fracturing. A little hydraulic fracture determines the least principal stress, and so we actually have some of these dots are right on top of each other. And we transform this data over here, and this is the stress path. So the slope is the stress path. We had no data early on, but interestingly, if you actually extrapolate that slope back to the initial pore pressure, it fell right on the normal faulting line. So what did this say? It said, okay, we had active normal faulting system here, active normal faults in the Gulf of Mexico, but as depletion occurred, those normal faults sealed up, they became more stable, but as depletion occurred, the porosity reduced due to this inelastic compaction. Okay, so that's how we use all this. Okay, and I need to speed up. So now, what does this have to do with earthquakes? So this paper we published last year demonstrated that, in fact, there are only earthquakes where there had been no prior production. And so the title of the paper was Prior Production Limits the Occurrence of the Earthquakes. And you can see that in this diagram right here. Here, the green dots show the saline aquifer in normal faulting equilibrium. And then we had data that was in the public domain from 3 wells up here, which are depleted, and they're way over here. So all these faults that are affected by injection are not active because the production stabilized those faults before the injection began. Okay? And so in most cases, from a geomechanical point of view, in a normal faulting environment, depleted oil and gas reservoirs, should be suitable for both CO2 injection and for hydrogen storage. So I'll go through this part really fast. Okay. Anyway, we'll show for the 6 minutes. I had no idea what to do with the open session that follows my talk, so I just was talking more slowly. I told this to Marta. She says, "Oh, you'll know what to do," and I guess I did. Anyway, here's an example from the McAllen Ranch. And here's the stress path, and what we see, is a significant reduction in porosity, and of course there'll be a significant reduction in permeability as well. So when you look at these depleted reservoirs, you have to characterize them in their current state before you start modeling them for injecting anything. Okay, it's a small point, but an important one. Okay, just a couple words about Groningen then. Okay, Groningen is very unusual. Okay, and obviously of great concern, a tremendous resource, but a lot of seismicity. And the seismicity falls along the typical Gutenberg-Richter line, the larger the magnitude, the fewer the earthquakes, and then sort of tails off. The biggest earthquake has been a magnitude 3.6, if I got it right, okay? And the tectonic setting is really pretty straightforward, north-northwest compression, it's normal faulting, and the faults are striking more or less parallel to the regional stress field. And the important point, though, is the thickness of the reservoir. The thickness of the reservoir is a couple of 100 meters. It's salt above and shaly formations both above and below. And for a source dimension of a couple of 100 meters, one would expect earthquakes, on the order of magnitude 3, or, you could push it and maybe say a little bit larger, 3.5, 4 is pretty reasonable. And that the reason the earthquakes are restricted to the reservoir in Groningen, which of course was only known once they put the seismometers down in the reservoir, is in fact these geologic constraints. This is where you're changing the stress path, and I'll show you that in just a minute. And above and below, we have the shale reservoir, these shale formations, which are not in failure equilibrium. So the Tenbor and the Carboniferous shales below are actually barriers to fault propagation. And we've seen production-induced earthquakes in other places. This is the Valhall Reservoir in the North Sea, and there are earthquakes due to depletion. When we published the paper, we puzzled over the fact that the earthquakes seemed to be just above the reservoir. After we published the paper, the seismologists corrected the velocity model, and the earthquakes are in fact in the reservoir. And what we saw there is that the crest of the reservoir was in failure equilibrium, and in fact, these faults in the crest of the reservoir were not mapped by us, they were already, but the flank of the reservoir was stable, but had a very steep stress path, and so it started stable, but eventually came into normal faulting equilibrium. So they induced the earthquakes by spreading out, because they had this very high stress path, high initial stress path on the flank, but the crest was just in this failure equilibrium to begin with. Okay, so what about Groningen? So I was trying to understand Groningen in the context of what I've been talking about, and I went to one of the NOM reports, and this is compilations of data from different depleted gas fields. And what you can see is the data are really highly scattered. Nobody was collecting data because they weren't interested in this phenomenon. And so what I did is I threw away all the data except the Groningen data. And the Groningen data are these three measurements right here. Okay, and the initial pore pressure was 350 bars. So the stress data are not available until there's been significant depletion. However, by digging through some of the references in these NOM reports, I found this old paper by Mark Hedema and others, it's 25 years ago, and they were talking about severe mud losses during drilling at, at a pressure of, about 428 bars, I think it was, and that was right on the failure line. So the way I think about Groningen is it basically, just like the sort of these other cases I showed you, it started in normal faulting, and basically it has evolved, with a stress path right along the normal faulting line, right, with a slope of, this 0.67, or it could be larger, but the stresses can't go below it. So the takeaway message in Groningen is really pretty simple. It started in normal faulting equilibrium, and depletion has sort of kept it in normal faulting equilibrium. And so it's not a good place to inject anything at this point. It's not a good place to inject CO2. It's not a good place to inject hydrogen. And it's not even a good place to inject, say, water to try to maintain pressure. It is seismically active. But it's not going to produce big earthquakes because geometrically the faults are limited in size. And this is the final thing I want to say, is when you look at the various depleted reservoirs available that you will consider, many of them will not be in failure equilibrium. They will have the stress paths that are, that have moved you away from failure equilibrium, and you can tell that very simply by simply looking at the pore pressure and looking at the least principal stress and knowing what the overburden is. It's really not hard to sort of qualify one of these depleted reservoirs as being potentially suitable for a cyclic process of raising the fluid pressure, during the summer when you're injecting hydrogen and depleting the fluid pressure. And so you start with a much more stable system, and then you can allow the pressure to fluctuate seasonally or more rapidly as long as you stay within these operational bounds. So don't worry. Be happy. I'm not saying you don't have problems. There are all sorts of other issues. But from a geomechanical point of view, you have a lot of candidate sites. And it's just going to... So I was very high on this long list. I was very high on the field tests. I think field tests are wonderful because they organize your thinking and they make you do all those other things in order to do the field test. But you have places that could be very, very suitable for hydrogen storage, other things being equal. So thank you very much.
Thank you very much. Excellent. In fact, the salt cavern visit we are going to have tomorrow is in the proximity of Groningen field that they are doing the pilot test. So that's...
Thank you very much for your great presentation, Rene, Politecnico di Milano. I want to refer to the concept of storage capacity. Clearly, if you base the storage capacity on, let's say, volume of the reservoir is overestimation. Instead, we can base the estimation of storage capacity on pressure buildup. Then we have the limitations of the stress, injection rate. Do you see any concern related to estimation of storage capacity based on pressure buildup if we are thinking about hydrogen storage? Because I know it is applicable for CO2 sequestration. What about hydrogen storage?
Well, you know how much depletion there was. So let's just say there's 20 bars, 30 bars of depletion. That's going to sort of set the scale for you, right? You're not going to let the pressure get too low. You're going to have a cushion gas in there. And you're not going to want the pressure to exceed certainly the initial pressure. And there's some other geomechanics a little bit. But it's going to give you, by doing the characterization, it's going to give you the operating range. And if that operating range is too small, then it's not going to be suitable, right? But I think you'll have the ability to find operating ranges, that work for seasonal storage. Because gas is really good. The reason gas is good is you've got a seal that's sealed a small molecule, and gas reservoirs often get pulled down. The depletion in a gas reservoir is often much larger than in oil reservoirs. Okay, and some of these reservoirs will be sufficiently depleted that it gives you a very reasonable operating range.
Yeah, Bart Lowens, Shell. Thanks a lot. It's more now a confirmation because I was wondering the entire time, but in the end I think you mentioned, but let me confirm. So you're saying that in contrast to CO2, which you hope to inject and it will stay there, and maybe in many cases water injection as well, when we talk about hydrogen, this is cyclic basic. So really if you stay within these boundaries, there's no difference upon a single charge or repeated charging and depletion?
A couple of us were talking about this earlier. There may be issues with respect to fatigue of the wells or infrastructure, but from a geomechanically, perspective, I don't see any issue. And I think Catherine's going to talk a little bit about natural gas storage. And I think it is, as Stefan mentioned on Monday, I think it's the right analog for us to think about. Depleted gas reservoirs being used for natural gas storage may be the best analog for what's being considered for hydrogen.
Hi, my name is Silke from IBN. Thank you for this great talk. I recently heard this podcast about nitrogen injection in the Groningen field to enhance natural gas recovery and to be able to control the stress in the field. And what do you think about that?
I think it's a bad idea because you don't need my diagram to know that the faults are already active, right? The faults are active, they're moving, they're on a failure stress path, and so raising fluid pressure when the faults are already active. Now, it'd be really nice to know exactly where that reservoir started, and we don't. But we know where it is today, and today it is on the failure, it is on the failure line. So, in 2020 hindsight, it's a possibility that you could argue that Groningen, they could have done different things at the beginning and managed the reservoir production in a different way. But where it is right now, it is what it is. I just don't think the earthquakes are going to be. I think we've had the biggest earthquake. I think 3.6 is about it. Maybe, I don't know. Maybe and this MMAX report's going to be written and with all the probabilistic mumbo jumbo and all the rest. The seismicity is going to continue. It's just not going to get very large. And that's easy for me to say, but it does affect people, and so it's a political issue.
Thank you.
Karen Fontine, Ministry of Economic Affairs and Climate in the Netherlands. I've got two small questions. One is, so you say basically Groningen was really at a normal faulting regime already from the start.
I think so, but
and how do you then explain that there were no seismic events up to 1991?
Yeah.
Or no recorded seismic events, let's put it like that. There were some tremors being felt in the 80s, so that's known, but there's still 20 years from 1963-4 to the 80s.
Yeah, and the way you do that is you take this diagram and you cheat a little bit. For example, if the friction were a little bit higher, that blue line would be a little bit lower. if this is too conservative and you started up here, you might have had to come down a bit before you hit it. You can explain it, but it's just hypothetical. You know, we just don't know. You know, we just don't know. But it's what I'm saying is I don't think that discounts this, but we can't make a complete argument because we just don't know where we started and how it evolved.
Okay. Then the other small question. So basically, if I understand your talk right, if you're thinking about gas storage or H2 storage in the Netherlands, you are actually looking for gas fields that have not experienced any seismicity during production.
Yes.
And those are the fields that you want to consider.
Yes.
Because next to Groningen, we've got 30 other small gas fields that have experienced seismicity during the production
Correct.
interval.
Right.
There's also a lot of others that
Right.
have not experienced any recordable seismicity. Of course, it depends on your
Right.
network.
Right. No, that's exactly correct. You know, if you're on the failure line, you don't have an operating window. You are, in fact. But what I'm saying is, if we go to, let's go to, let's look at one with real. Let's look at real data. Okay, like this. Okay, so if you're here, right, then your operating window is something like this, right? You have, you know, a few hundred bars, right, of operating window before you have to worry about earthquakes. But if you're on the red line, you don't have, and that's not a field that should be considered. That's right. Very straightforward.
Yeah, Remco Groenenberg from TNO. Thank you for a very interesting presentation. I have one question and one remark. Maybe the question first, also coming back to what Karen said. So I was looking for some selection criteria. So basically to be able to funnel from a large number of depleted oil and gas fields, for instance, to a smaller number. And at least I understand from you that past presence of seismicity is basically a no-go. Are there other selection criteria that you can think of in this regard?
Right. Well, the other, you know, I didn't show the equation, but the equation for this line is really, you know, trivially simple. You need to know the overburden. You need to know the magnitude of the least principal stress. You know, are you on? And that's easy to measure with just little mini fracs and pore pressure. And that'll tell you if you're, even if there are no earthquakes, if you're close to that line, you probably don't want to consider that reservoir either. Okay? Right. But, you know, the reason for showing, you know, real data as well as the, you know, the hypothetical cases is, you know, this is, you know, if you can't find a good place for hydrogen storage in the Netherlands, South Texas is going to work out just fine. So no, but I'm serious. The way this evolves is controlled by local geology, and I don't know the fraction of your depleted gas reservoirs that are associated with seismicity, but it's a straightforward screening criterion that you can use.
Maybe the remark then. So your example of Oklahoma made me think about the Castor project in eastern Spain. This was an underground gas storage that was being developed, and during injection of the cushion gas, they experienced magnitude 4 earthquakes.
Yep.
And it was basically cancelled in the end.
Yeah.
Are you familiar with it?
Yeah. I sort of got involved in Castor a little bit. What happened in Castor was unfortunate. It was a depleted oil reservoir, and the pressure went down. But it was like 20 years after the oil production stopped and their gas production started. And what happened is the aquifer brought back the pressure to the initial pressure. So Castor was depleted at the end of oil production, but was not depleted in a pressure sense when they started the gas injection. And that's the error they made, is they didn't pay enough attention to the pressure at the time they started injection. They were still thinking the pressure would be low, and it wasn't. And that's why they got the induced seismicity.
I think it was also a calcified limestone, and it was even close to basement as well. So
there's a lot of debate because, you know, the earthquakes are offshore, right? And they weren't very big, and they were only recorded by a couple of stations. And so there's about 4 or 5 published models, you know, putting the earthquakes in different places. Were they deep? Were they in the reservoir? And so on. But there's no question that Castor is it's not suitable for gas storage. But from a reservoir point of view, it's because the pressure had rebounded over time. Okay.
Good morning. Thanks for your talk. Hein Vergent, State Supervision of Mines. So I've got a caveat, maybe, and a question. The first comment is on the graph you showed with magnitude versus damage. In the Netherlands, of course, we also have what's called the amplification effect. I'm sure you're aware of this, where the waterlogged soils amplify seismic waves, very much like the Mexico City earthquake in the 1960s. My question is, I really appreciate you looking a little bit more at the human perspective, the effect that these quakes have on the populace without actually damaging too much. We know that in Groningen, stress-related health issues are a big issue. Is there something similar being done in the Oklahoma cases, and is there data there on the mental effect of these quakes?
Interesting point.
I don't know, but I would doubt it. It's
too luxury.
It's just a different perspective on these kinds of things. So and it's true. You know, we get hung up on magnitude, but that's the hazard. But it's the risk you care about, and how that hazard is reflected in damage and perhaps emotional distress as well. So
we have plenty questions online as well. But Milad, go ahead, introduce yourself. But
Milad, PhD candidate, TU Delft. Thanks for a great talk. I got two questions. The first one is, you called Groningen gas field unusual case. And then I was going to ask, is there any reason, like mechanically, that you can call it and relate it to this unusual case? Like, is it differential compaction helping there for earthquake or other stuff?
yeah, this is where I kind of differ from the NAM geomechanics guys.
here, Mark. Yeah, good.
Just, if this is the free surface and this is a depleting reservoir, and if you think about this as an inclusion, right? It's surrounded by a rubber balloon, and the pressure is going down, and this is all elastic. As that pressure goes down, the stress gets more compressive above and below, and then over here, the horizontal stresses go down. And so if you're in a compressional environment, the change in stress here would enhance faulting, or down here. If you're in an extensional environment, the change in stress out here would enhance normal faulting. So now you're in a normal faulting situation. And in fact, this is very schematic, and you have a real stress concentration right at the edge. So the NAM model is, they have a fault, you have an offset reservoir, like this, and then you get these stress concentrations interacting from the termination of the reservoir at the position of the fault, okay? Now, you know, this is perfectly reasonable model, but, and that's why you have faulting, but this is saying it's a more, you know, it's actually what's happening inside the reservoir, and it's not just the edges. And of course, those two models are not exclusive. They both could be right, or both could be wrong. Okay, but this is the differential compaction model that I know the Shell side of NAM believes, and Exxon's not been. I haven't seen their models for a long time, and they're strange models, and I have some other problems with those. But you know, people are just doing the best they can and trying to explain what they see. So.
Can I ask the second one, or?
No. We have 100 questions or so. Just go ahead there, and then I need also online. 12,000 people participated his class, so imagine how many questions.
Okay, thanks Mark for the interesting presentation. Joachim from TNO. I have a question. We have been looking a lot of underground gas storages in the Netherlands, and just sort of see how much hydrogen they could store, how they could be withdrawn, injected. But then we see the amount of energy you can store in natural gas is 3 times more than hydrogen. So and then it's just the possibility that probably if you want to extract more, have a more working volume, that you have to lower the pressure. What is your opinion about if there is a field that has not had any seismic activity, and then you say, okay, but now for hydrogen storage, you have to lower the pressure, lower the felt has felt, because probably there's still some gas in it. So what would be the chance that you have a limit there?
It's really easy. Pressure is the problem. So just, you'll have to inject more gas, more hydrogen, right? But you just watch the pressure, right? And whatever your models show you for the pressure change, that will tell you, if you're staying in this safe operational range between where you are today and where the limits on injection are. So just follow the pressure, with your reservoir models, and regardless of what kind of gas you're using, it's really pretty straightforward.
I take one question online, and then we go to break. We list all these questions. Marty is taking a kind of note about all these questions, but we may...
I never agreed to answer them all, Okay.
No, just one thing, Mark. They said that you were a bit pessimistic about utilization of aquifers for storage, gas storage.
I'm very pessimistic. Okay.
So they said that, is it possible that we produce a bit water and then, maintain the reservoir and then do the pressure maintenance?
Yeah, but the question is, what do you do with the water?
Exactly.
Of course. And of course, there's a big project going on in Australia, Gorgon, which was also listed as a successful project. I think I would call it things that are decades overdue and tens of billions of dollars of over budget, and operating far below planned capacity is not being successful, but it's a matter of definition. What do you do with the water? So that's really, and let me repeat, some saline aquifers will be fine, but it's going to take work to determine what you do before you do it. We talk about all the economic incentives that government policies can advance CO2 sequestration. So one of the dangers, probably less likely to happen in the Netherlands than in West Texas, but if people see an economic incentive for injecting CO2 in the ground, they're going to inject CO2 in the ground. And I call these the pump and pray guys. They're going to pump and they're going to pray that nothing happens, right? And that really could be damaging. It just takes a few cases. It's like fracking, right? A few irresponsible fracking operations, created a sense in the public that the world was going to come to the end. Well, we've done 300,000 wells, millions of frac stages, and the world hasn't come to an end. But if you have good regulations and the regulations are followed and the operators follow best practice, but I'm afraid that with economic incentives, if people just go after this without doing the characterization, bad things are going to happen. And
thanks a lot. We could have run this till midnight, but thank you very much, Mark, for this excellent talk.